Students, after reading this chapter, you will be able to understand the following concepts: the concept of multiple regression, estimation of multiple regression, F-tests, prediction in multiple regression model, and selection of a model, which means how to select a model. So let me introduce the subject to you. I am sure you would understand and you would recollect that in regression analysis, we study the relationship between two or more variables. There are two types of regression model, namely simple regression model and multiple regression models. The relationship between two variables is studied in simple regression model. In multiple regression model, we basically study the relationship between more than two variables. In reality, most of the studies in econometrics require multiple regression model. For example, we want to understand the factors that determine the productivity of a crop. We can propose that the productivity of the crop is influenced by quality of the seed, soil fertility, use of fertilizer, rainfall, etc. In such cases, we employ multiple regression models to study the productivity of a crop.
Multiple regression analysis is often used to predict unknown value of a variable from a given value of two or more variables. We call the predicted variable as predict and or dependent variable, and the values used for prediction are as predictors or independent or explanatory variables. So we can predict the values of y for given values of x2, x3, so on up to xk in multiple regression models. We can add more independent variables to simple linear regression model to obtain multiple regression model. A multiple regression model with k independent variables can be represented as given below, where we have yi equal to beta 1 plus beta 2 x2 plus beta 3 x3 so on up to beta k xk plus ui. The estimated equation for the above regression model is as follows, which is yi hat equal to beta 1 hat plus beta 2 hat x2 plus beta 3 hat x3 so on up to beta k hat xk. Meaning of regression coefficients. The parameters beta j hat, where j takes the values from 1 to k, are known as regression coefficients. The regression coefficient beta 1 hat is the intercept, and beta 2 hat, beta 3 hat up to beta k hat are analogous to slope coefficient in simple linear regression equation. Their interpretation is also similar to that of the slope in simple regression model. So if beta 2 hat is equal to 3.72, this would mean that y will increase by 3.72 units if x2 increase by 1 unit while holding other independent variables as constant. Therefore, generally speaking, the parameter beta j represents the expected change in dependent variable y per unit change in xj when all the remaining independent variables xi, I not equal to j, are held constant. Graphical representation of multiple regression. A simple linear regression model can be represented graphically as a straight line in a two-dimensional space. A multiple regression model with two independent variables yi hat equal to beta 1 hat plus beta 2 hat x2 plus beta 3 at x3 can be represented as a plane in three-dimensional space in such a way that the sum of squared residuals is minimized. The residuals can be captured by the distance from the points to the plane parallel to the y-axis. When we have k number of regressors, mathematicians describe such multiple regression model as a hyperplane in the k-dimensional space of the independent variables xi. Estimating regression coefficient using least squares estimates. We consider a multiple regression model which has k number of explanatory variables. Let us write the model as yi is equal to beta 1 plus beta 2 x2 plus beta 3 x3 plus so on up to beta k xk plus ui. Suppose the number of observations n is greater than the number of variables k, that means n is greater than k, then the least square methods can be used to estimate the coefficients in this above model. We can formulate the least square function of the above model as given below. Let us define it as L equal to summation ui square, where I is from 1 to n, which is equal to summation I 1 to n of bracket yi minus beta 1 minus summation of beta j xij, where j is from 2 to k whole square. The least square function is differentiated with respect to beta 1 up to beta j, and we obtain the following equations. Derivative of L with respect to beta 1 given beta 2k, beta 2 to beta k is equal to minus 2 summation over I from 1 to n into yi minus beta 1 hat minus summation beta 1 hat into xij, where j is from 2 to k whole square equal to 0. And if you keep on taking these differentiations of L with respect to each of these betas, then we get derivative of L with respect to derivative of beta j given beta 1 hat so on up to beta k hat is equal to minus 2 summation over I equal to 1 to n. In the bracket we have yi minus beta 1 hat minus summation of beta j hat into xij, and this summation is over j from 2 to k into xij equal to 0, where j takes the values from 2 to k. Solving the above two equations, we get the following least square normal equations. The above normal equations are solved to obtain the least square estimators of the regression coefficients. Matrix formulation of least squares estimates. Suppose the multiple regression model with k number of independent variables is written as we described earlier, as yi is equal to beta 1 plus beta 2 xi2 plus beta 3 xi3 so on up to beta k xik plus ui, where I takes the values from 1 to n. The term in this equation ui is known as stochastic error term. The conditional expected value of the stochastic error term is 0. In other words, the mean value of the error term for given explanatory variables is 0. We can write it as expected value of ui given xi is equal to 0 for all I. Similarly, the second assumption is that the variance of a stochastic disturbance term is constant for all observations for a given value of explanatory variables. For this assumption is known as homoscedasticity or equal variance and can be written as variance of ui is equal to sigma square for all I. So students, I have given you these assumptions of the basic multiple linear regression models. We have other assumptions also which we would discuss subsequently. Another assumption is that the covariance between two error terms is 0. That is, any two error terms are uncorrelated. This assumption is known as assumption of no autocorrelation or no serial correlation. And this can be written as covariance of ui and uj is equal to 0 for all I not equal to j. The fourth assumption is that the explanatory variables xi2, xi3, xik are assumed to be fixed in repeated samples. So we assumed that the explanatory variables are not stochastic. The fifth assumption is that the explanatory variables xi2, xi3, xik are linearly independent across k. That is, there is no correlation among explanatory variables. This assumption is known as no multicollinearity among explanatory variables. The estimation of multiple linear regression model is easier in matrix form representation. So we convert the regression model and the assumptions in matrix form. In matrix form, we can write the y scalar as or y vector as y1, y2 up to yn as the dependent variable y vector. On the right hand side, we have the X matrix, which has the first column as ones. The second column starts from x21, x32, xn1. Sorry, it is from x21, x31, xn1. In the next column, we have the values from x22, x32, xn2, and the last column has x2k, x3k up to xnk. The beta coefficient vector is beta 1, beta 2 up to beta k, and the error term vector is u1, u2 to uk or un. The above matrix formulation of multiple linear regression model can be simplified as follows. We can write this as y is equal to x beta plus u. The classical assumptions in matrix form representation are as follows. First, expected value of u is equal to 0. Second, variance of u is equal to expected value of u minus expected value of u into u minus expected value of u prime, which implies is equal to expected value of u prime and is equal to sigma square into in, where in is the identity matrix of the order n. The third assumption is that x is fixed and non-stochastic. Fourth assumption is that x has full column rank, and full column rank means that n is greater than k. Our objective is to find the vectors of least squares estimators that would minimize the following least square function. The function now is written as L equal to ui hat square, where summation is from 1 to n, and this is equal to u hat prime into u hat, which is equal to y minus x beta hat prime into y minus x beta hat. Here we can see that u prime u is equal to y minus x beta hat prime into y minus x beta hat, and if you just take these primes, you get y prime minus beta hat prime into x prime, and this is being multiplied by y minus x beta hat. So the terms which we obtain are y prime y minus y prime x beta hat minus beta hat prime into x prime y plus beta hat prime into x prime x beta hat. Now this is equal to y prime y minus 2y prime x beta hat plus beta hat prime into x prime x beta hat. Please note that beta hat prime x prime y is a scalar, and hence beta hat prime x prime y whole prime is same as y prime x beta hat. We differentiate the least square function with respect to beta hat and equate it to 0, which means we take derivative of L with respect to beta hat and put it equal to 0. We have used two results from metric differential calculus to solve the above first order condition. The results used are the derivative of A into B upon derivative of B, which means derivative of AB with respect to B, is equal to A prime. and secondly, that the derivative of b prime ab with respect to b is equal to twice ab. Using these results, if we take the derivative of L with respect to beta hat, we get minus 2 x prime y plus 2 x prime x beta hat equal to 0. Solving the above equation, we obtain the OLS estimator, which is beta hat comes out to be equal to x prime x inverse x prime y. Since we assumed that X has full column rank K, the matrix X prime X inverse exists. The second order conditions for a minimum are also satisfied, which is that second derivative of L with respect to beta hat and with respect to beta hat prime is equal to twice X prime X, and this is greater than 0 because X is a positive definite matrix. X prime X is a positive definite matrix. Variance of regression coefficients. We know that beta hat is equal to X prime X inverse X prime Y. So if you substitute the value of Y, which is X beta plus U, we get beta hat equal to X prime X inverse X prime into X beta plus U, and this comes out to be equal to beta plus X prime X inverse X prime U. Now taking expectation both the sides, we get expected value of beta hat equal to expectation of beta plus X prime X inverse X prime U, and therefore this is equal to beta plus X prime X inverse X prime expected value of U, and hence is equal to beta, because beta hat therefore is proved to be unbiased estimator of beta. But this previous result we have obtained because we know expected value of mu is equal to 0. How do we find out the variance of beta hat? Let us do it here in this slide. We can define variance of beta hat to be equal to expected value of beta hat minus beta into beta hat minus beta whole prime. Now, on substitution of the value of beta hat, we obtain this to be equal to expected value of X prime X inverse X prime U into X prime X inverse X prime U prime. So this is equal to expected value of X prime X inverse X prime U prime X into X prime X inverse. Hence this is equal to X prime X inverse X prime expected value of U prime into X prime X inverse. Now this is equal to X prime X inverse into X prime sigma square IN into X prime X inverse. Now taking sigma square out, we get this equal to sigma square into X prime X inverse, because I on multiplication between X prime and X gives us X prime X, which is cancelled out with one of the inverse values. So finally, we get variance of beta hat to be equal to sigma square into X prime X inverse. Now, since the unbiased estimator of sigma square is given by sigma hat square equal to U hat prime U hat upon n minus k. Testing the overall significance of multiple regression model. While it is important to test individual regression coefficient for their statistical significance, it is equally necessary to test the appropriateness of the multiple regression models as a whole. We need to know the joint influence of all the explanatory variables on the dependent variable. In other words, we need to test the overall significance of the regression model. Now this can be done by using the analysis of variance or ANOVA technique. It tests whether the dependent variable is linearly related to all the explanatory variables. The overall significance of the multiple regression model cannot be tested by testing the significance of individual coefficients. This means that the significance of individual regression coefficient does not imply the overall significance of multiple regression model. This is because in testing the significance of individual coefficient, we assume that each test is drawn from different sample. So, if we conduct the joint hypothesis and use the same sample data, we will be violating the assumptions of test procedure. Consider a k-variable linear regression model. yi is equal to beta 1 plus beta 2 x2 so on plus beta k xk plus ui. This is the model which we have been using again and again. Now we want to simultaneously test whether all the slope coefficients beta 2, beta 3, beta k are 0. In other words, the null hypothesis is hypothesis H0 is equal to beta 2 equal to beta 3 equal to so on up to beta k equal to 0. The alternative hypothesis is that at least one of the slope coefficients is not equal to 0. The analysis of variance technique can be employed for such a test, and you can refer to this ANOVA table in this. We know that total sum of the squares TSS is equal to explained sum of the squares ESS plus residual sum of the squares RSS. In terms of algebraic expression, it can be written as follows. Summation yi square is equal to beta 2 hat summation yi into x2i plus beta 3 hat summation yi into x3i plus so on up to beta k hat into summation yi xki plus summation ui hat square. The total sum of the squares TSS has n-1 degrees of freedom. Explained sum of the squares ESS has k-1 degrees of freedom, and residual sum of the squares RSS has n-k degrees of freedom. We assume that the error term ui follows normal distribution. When the null hypothesis is beta 2 is equal to beta 3 equal to beta k equal to 0, in bracket we have beta 1 hat into summation yi x1i plus so on up to beta k hat into summation yi xki whole divided by k minus 1, and in the denominator we have summation ui hat square divided by n minus k. In this expression, the numerator is explained sum of the squares ESS divided by degrees of freedom, and in the denominator we have the residual sum of the squares RSS divided by the degrees of freedom df. This f statistics follows f distribution with k minus 1 as degrees of freedom in the numerator and n minus k as the degree of freedom in the denominator. The null hypothesis is rejected at a predetermined level of significance, say alpha, if the individual f statistic is greater than the critical f value. So when the null hypothesis is rejected, we say that the multiple regression is an appropriate model. When the f test is significant, it means that the dependent variable and at least one of the explanatory variable has significant linear relationship. In case the f statistics is less than the critical f value, then the null hypothesis cannot be rejected, and we conclude that the multiple regression models is not appropriate for the model. One can also look at the p-value of the f statistics, and if they are low, the null hypothesis can be rejected as well. F test and R square. We can express the F statistics in terms of R square as well. We know that R square is equal to ESS upon TSS and is equal to 1 minus RSS upon TSS. So F is equal to ESS divided by K minus 1 upon RSS divided by N minus K. Now this is equal to N minus K into ESS upon TSS. In the denominator we have K minus 1 into 1 minus ESS upon TSS. Now this on simplification comes out to be N minus K upon K minus 1 into R square upon 1 minus R square. Therefore, F can be written as equal to R square upon K minus 1 upon 1 minus R square upon N minus K. We can thus draw a relationship between F statistics and R square. In the extreme cases, when R square is equal to 0, the F statistic is 0. And when R square is equal to 1, the F statistics is infinite. So when the R square increases, the value of F statistics increases as well. Therefore, the F test, which tests the overall significance of the regression model, also tests the significance of R square. Prediction for multiple regression model. The issue of prediction involves forecasting the unknown value of a dependent variable y for a given value of independent variable or variables x. In simple linear regression model, we predict the value of a dependent variable for a given value of explanatory variable. The same concept of prediction could be well extended for multiple regression model as well. Consider the scalar form of the following estimated multiple regression model, which is same as yi hat equal to beta 0 hat plus beta 1 hat x1i so on up to beta k hat xki plus ui. We use matrix notation to write the above equation in more compact form, and we can write it as yi hat is equal to xi prime into beta hat, where xi prime is equal to 1 comma x1i comma x2i up to xki, and beta hat is equal to beta 0 hat, beta 1 hat, beta k hat, which is a column vector. Slide 30, mean prediction. The mean prediction of the dependent variable y given the values of x0 are, expected value of yi given x0 prime is equal to mu hat y given x0, which is equal to yi upon x0 prime and is equal to x0 prime into beta hat, where x0 in this case is a column vector 1 x01 x02 to x0k. The variance of the mean prediction can be obtained as given below, which is variance of y0 hat given x0 prime is equal to sigma square into x0 prime into x prime x inverse x0, where sigma square is the variance of ui, which need to be replaced by its unbiased estimator sigma hat square. x0 prime are given values of the variable x, and x prime x is the matrix given as below, which is x prime x equal to a 3 by 3 matrix, and we have in fact the order of the matrix will depend upon the value of k. So we have the diagonal values and the off diagonal values. I'm sure you can see it from this table from this matrix which we have shown here. For the multiple linear regression model, 100 into 1 minus alpha % confidence interval on the mean response at the point x01, x02 to x0k is denoted as mu hat or mu y hat given x0 minus T alpha by 2 comma n minus p under root of sigma hat square into x0 prime into x prime x inverse x0. This is less than or equal to mu prime or mu y prime upon x0 or mu y prime given x0, which is less than or equal to mu y hat given x0 and is less than or equal to mu y hat given x0 plus T alpha by 2 and n minus p into under root of sigma hat square into x0 prime into x prime x inverse x0. Individual prediction. The individual prediction of a dependent variable y, which is equal to y0 when the explanative variable x equal to x0, are given by y0 hat equal to x0 prime beta hat. It could also be written as y0 given x0 prime equal to x0 prime beta hat. The mean prediction and the individual prediction are the same. However, their difference lies in their variances. The variance of the individual prediction can be obtained as given below, which is that variance of y0 given x0 is equal to sigma square into 1 plus x0 prime into x prime x inverse x0, where variance of y0 given x0 is equal to expected value of y0 minus y0 hat given x whole raised to the power 2 or square. We need to replace sigma square by its unbiased estimator sigma hat square. 100 into 1 minus alpha % prediction interval for this future observation then is that we can say y0 is greater than or equal to y0 hat minus T alpha by 2 n minus p into under root of sigma hat square into 1 plus x0 prime into x prime x inverse x0, and this is less than or equal to y0 hat plus T alpha by 2 n minus p into under root of sigma hat square into 1 plus x0 prime into x prime x inverse x0. Choosing the best model. It is possible that there could be several competing models for forecasting purposes. Our task is to choose the best model on the basis of some criteria. We need to distinguish the difference between in-sample and out-of-sample forecasting. In the in-sample forecast, the concern relates to how well the chosen model fits the given data set. In the out-of-sample forecast, our concern relates to how a fitted model predicts the future values of the dependent variable for a given value of explanatory variables. We discuss the following selection criteria for choosing the best model for forecasting purposes. The R-square criterion. It is a popular measure of goodness of fit in a regression model. It is defined as follows: R square is equal to ESS upon TSS and is equal to 1 up minus RSS upon TSS. I'm sure you know where ESS is explained sum of the squares, RSS is residual sum of the squares, and TSS is total sum of the squares. The value of R square lies between 0 and 1. So if the model fits the data well, the value of R square will be high. However, since R square is a measure of in-sample goodness of fit, it may not forecast well for out-of-sample observations. The value of R square increases as the number of explanatory variable increases, but this increases the variance of forecast error. Only when competing models have the same number of explanatory variables, R square can be used to compare them. Adjusted R square. The value of R square will increase when more and more number of explanatory variables are added to the regression model. An adjusted R square was introduced by Henry Thiel to add penalty for the increase in the number of explanatory variables. And it is therefore defined as follows. So R bar square is equal to 1 minus RSS divided by n minus k and the whole divided by TSS by n minus 1. This on simplification comes out to be equal to 1 minus R square into n minus 1 upon n minus k. It is clearly seen that R bar square is less than R square. Adjusted R square is better than R square for any comparative purposes. However, the number of explanatory variables must be same for comparison to be valid. The AIC criterion imposes a harsher penalty for addition of more variables in the model than the adjusted R square. It is defined as follows. AIC is equal to e raised to power 2k divided by n into summation mu I hat square by n. Now this is equal to e raised to power 2k by n into RSS by n, where k is the number of explanatory variables including the intercept and n is the number of observations. The above notation can be rewritten as ln AIC is equal to 2k by n plus ln RSS by n, where ln AIC is natural log of AIC and 2k by n is known as the penalty factor. The AIC criterion can be used to compare both the in-sample and out-of-sample forecasting performance. When two or more models are compared, the one with lowest value of AIC is chosen as the preferred model. SIC, Schwartz Information Criterion. Another criterion similar to the AIC is the SIC criteria. It is defined as SIC is equal to n raised to the power k by n into summation mu hat square divided by n, which is same as n raised to the power k by n into RSS upon n. And in log form it can be written as ln SIC is equal to k by n log n plus ln into RSS upon n. Now where knn into ln is the penalty factor, or ln n you may say. In comparing various competing models, the model with lowest SIC is chosen as the preferred model for both in-sample and out-of-sample forecast. The penalty imposed in SIC is harsher than that in AIC. Let us take a hypothetical linear relationship between a dependent variable y and two explanatory variables x1 and x2 to understand what we have learned so far in this module. So we have a column of y values, we have x1 values, we have the values on x2 in this table which you can see in your slide. Now based on this table, answer the following questions. First, find the estimated regression line by finding the regression coefficients by solving the normal equations. Second, calculate the regression coefficient using the matrix approach. Third, find the variance and the standard error of the regression coefficients. Fourth, find the mean prediction and individual prediction of the dependent variable y when the explanatory variables are x1 is equal to 60 and x2 is equal to 230 respectively. Calculate the variance of the mean and individual prediction at x1 is equal to 60 and x2 is equal to 230. In this slide, we have provided you the solution in this tabular form where we have different columns calculating or giving you values of y, x1, x2, and then calculating x1 square, x2 square, x1, x2, x1y, and x2y. You can see in the last row, we have the summation signs. For your convenience, we have reproduced the normal equations below, which are as follows. You can use these normal equations to calculate the values of the coefficients. Substituting the values of the various summations into these normal equations, we get these three normal equations which are before you. From these normal equations, we find that the regression coefficients can be calculated using the matrix approach directly also, where we know that beta hat is equal to x prime x inverse x prime y. So you have these vectors and matrices. On the left hand side, we have the y vector of the order 10 by 1. Then we have the x matrix of 10 by 3 order. Then we have the beta prime or beta hat vector of 3 by 1, which is beta 0 hat. So we have the beta hat vector, which is beta 0 hat, beta 1 hat, and beta 2 hat. And we have the u hat vector of the order 10 by 1, which contains the values from u1 to u10. You can see how we have calculated the x prime x matrix, where we have the x matrix, we have the prime of it, we have the x matrix, and we have multiplied these matrices, and we obtain the product matrix, where you can see we have the diagonal elements starting from n, and then summation x1i square and summation x2i square, and we have the off diagonal elements as summation x1i, summation x2i, and so on. Similarly, we have the substitution of these values, and we get x prime x matrix, and you have the elements starting from the first cell value of 10 to the last cell value of 722,881. Here you can see now how we have also calculated the cofactor matrix of x prime x inverse. It is before you. We have the determinant of x prime x, which is equal to 21519068878. Using these together, we have calculated the inverse of x prime x. Similarly, we have calculated x prime y. You can see that the product of x prime y is nothing but equal to sigma y, sigma x1iy into sigma x2iy. And on substitution of these values, we get x prime y equal to 2060132310 and 672720. Now, if you calculate your beta hat vector, which has beta 0 hat, beta 1 hat, and beta 2 hat, you substitute these values, and on simplification, we get on the right hand side minus 18.42948, 1.73226, and 0.6515923. So these are our values of beta 0 hat, beta 1 hat, and beta 2 hat in vector form. Similarly, we can calculate the variance covariance matrix for beta hat, which is defined as sigma hat square into x prime x inverse, and the sigma hat square here is defined to be equal to u prime or u hat prime into u hat upon n minus k. Now, if you substitute these values, what we obtain is nothing but sigma hat square comes out to be equal to 176.39142 in slide 50. You see sigma hat is equal to 176.39142. So our variance covariance matrix of beta hat comes out to be a simplified value on substitution of this sigma hat square value and other values, and it is in this matrix form which you can see is before you. The variance of the regression coefficients are given by the diagonal elements of this variance covariance matrix. Their standard errors are obtained by taking the square root of their variances. So if we want to know variance of beta 0 hat, variance of beta 1 hat, variance of beta 2 hat, it comes out from these diagonal elements, and they are equal to 139.0367, similarly 0.21469, and 0.004399 are the values. If you take the under root of these, we get standard errors. So standard error beta 0 hat, beta 1 hat, and beta 2 hat are also given in the vector in this slide. The fourth part of our question is the individual and mean predictions. They are same and it can be calculated as follows. That y0 hat is equal to mu y or mu y hat given x0, and this is equal to x0 prime into beta hat. Now on substitution of these values, we get y0 hat equal to 235.372349, which here we give you the solution to the fifth part, which is the variance of the mean prediction, which is given by variance of y0 hat given x0 prime, we know is equal to sigma square into x0 prime into x prime x inverse x0. On substitution of these values, you can find out that on simplification, we get this equal to 35.907. So the variance of the individual prediction is given by variance of y0 given x0, which is equal to sigma square into 1 plus x0 prime into x prime x inverse x0, and again this on substitution can be found out to be equal to 212.299.
We study the relationship between more than two variables in multiple regression model. Most of the studies in econometrics look for a relationship between more than two variables. The regression coefficients in multiple regression model can be interpreted in the same way as in the case of simple linear regression model. Geometrically, we have learned that multiple regression model can be described as a hyperplane in the k-dimensional space of the independent variables. You have also learned that the normal equations derived from least square techniques are solved to find the regression coefficients of the multiple regression model. We have also seen that how we can use the matrix formulation that provides another convenient method of finding regression coefficients. We have learned that the multiple regression model needs to be tested for the overall significance of the model using f-test. When the f-test is significant, it indicates that the dependent and independent variables have linear relationship. There are basically two kinds of prediction in multiple regression model, namely individual prediction and mean prediction, which we have learned. Both of them give the same results for mean but have different variances. I am sure you know we have learned that there are various selection criteria for choosing the most appropriate model for forecasting purposes. Some of them which we have discussed are R square, adjusted R square, AIC and SIC.